So now that we understand something about the age of the sun and how old that is, we can now start comparing one star to another and try to figure out which stars live longer or have longer lifetimes than others. The bottom line is we figure out how much fuel the star has, and then we figure out how fast it's using that fuel up, and we divide the two, and that will give us the lifetime. And we do all this in ratio to the sun and its lifetime. So to begin with, we're going to make an analogy between stars and cars. So we're going to first look at cars. Imagine the beginning of spring break, every student at our college got in his car or truck and drove away. Imagine also that there was a huge gas shortage so that each student filled up his car or truck with gas but could not buy any more on the day of travel. We will also imagine that everyone wants to get as far away from Hampden-Sydney as possible, as quickly as possible, in order to get to the coast of Florida or as far south as possible. Imagine everyone averages 60 miles an hour on the highway. We will use the following three cars to do our calculations. A 2007 Honda Civic Hybrid, which gets 51 miles to a gallon, has a tank size of 12 gallons. A 2007 Ford Ranger, two-wheel drive, 29 miles per gallon, tank size 17 gallons. And a 2007 Grand Cherokee, 8 cylinders, 15 miles per gallon at 21 gallon tank size. So if we just find the rate of fuel consumption in gallons per hour, assuming they're traveling at 60 miles per hour, put the values in the table below. Now in order to do that, we want to have an answer in gallons per hour, which is the rate of fuel consumption. Much like the luminosity of a star is the rate of its fuel consumption. And so let's calculate this for the first one, and then we'll go from there. So clearly, the better your gas mileage, the less fuel you're using. And so what we're going to do is we're going to say we're all traveling at 60 miles per hour, and we have our car has a gas mileage of 51 miles per gallon. So we're going to say that the rate of consumption is going to be equal to 60 miles per hour divided by 51 miles per gallon. You see why it's so important to put your units in, because this way you can see that the miles cancel and we're going to get gallons per hour, which is what we're interested in. So 60 divided by 51 is 1.18. So we're going to put that in. Notice how by dividing by miles per gallon, it's like you're multiplying the reciprocal, and so you get gallons in the numerator at the end. So now we can put this right down here for the first one. Okay, now let's do number 2 for the first one, and then I figure you can probably do the rest once you see me do the first one. Calculate the distance that they can travel on one tank of gas and put this in the table. Well, let's think about that. There's kind of two ways to do it, right? One way to do it is you can say we have a tank size and we have a miles per gallon, which is the rate of fuel, well, the fuel economy, and we can divide the tank size by that, and we should get the distance in miles, just like you would expect. Now I want to show you the other way to do it. You could say you want to travel 612 miles at a speed of 60 miles per hour, and you get the same thing, 10.2 hours. So I'm sure that now you can figure this out for the Ford Ranger and the Jeep Grand Cherokee, the 8-cylinder version. Notice that I picked cars that had, moderately bigger tanks, but much worse gas mileage. So that you can see that on something like the Honda Civic, you can actually travel further on a tank of gas than the Jeep Grand Cherokee, even though this is a bigger tank. Okay, and when I work that out, I get this. I probably should have rounded everything off to 2 significant figures because that's what we were given. So I probably should have written 1.2 here, and 2.1 here, and 4.0, and then 610, and so on. I just kept an extra digit because we were calculating things in terms of their intermediate values, and I wanted to make sure that things came out without too many round-off errors. So now that we understand how cars work in terms of running out of gas, which seems pretty common sense, the fuel for stars is hydrogen, and they use this fuel up in their nuclear fusion processes. Imagine the total energy in a star stars have is called E, and the rate at which they use it up, that energy, is given by the luminosity L. Then their main sequence lifetime is simply given by the formula T equals E over L. In other words, what's defined as the main sequence of a star is when it is using up its hydrogen fuel, making helium. After that, it can do other things depending on its mass. So what we're going to do is we're going to calculate the main sequence lifetime of a number of different stars. So the first thing we're going to assume is that the total energy amount of fuel is proportional to the mass. So for example, if the amount of fuel is in hydrogen, and you have a 2 solar mass star, it's got twice as much fuel than a 1 solar mass star, even if it doesn't use both solar masses or 1 solar mass, if you assume the same fraction is available. So here I say, because the amount of total mass of the core is some fixed fraction of the total mass. So, for example, let's take the sun as our standard. 1, and the main sequence lifetime is 10 billion years, and we know that because of the Lord Kelvin the sun work that we did before, and also from radioactive dating of how old the oldest rocks are. They're about 5 billion years old. Our sun's about 5 billion years old, and it appears to be smack in the middle of its life. So the star Sirius has a luminosity that's 25 times more than the sun's luminosity, and a mass that's double it. So we expect that its tank is twice as big, but its fuel economy is much worse. So what we're going to do is we're going to calculate the main sequence lifetime, and we're going to do it by showing all of our work down here for Sirius, and then you can do the same thing for Barnard's star. Okay, so for Sirius, we now know that the lifetime is proportional to the energy budget divided by the luminosity. And remember, this is lifetime, not age. It's lifetime. So Sirius' lifetime divided by the sun's lifetime must equal the ratio of the masses, because the ratio of the masses is the ratio of energies. That's essentially our tank. And our luminosity is the rate that we're using it up. So 25 solar luminosities divided by 1 solar luminosity. And so this equals 2 divided by 25. And 2 divided by 25 is 0.08. So what that means is that the lifetime of Sirius is about 8% the lifetime of the sun. That's what it means. it means its lifetime is going to be a lot shorter than the sun's lifetime. Now, the sun's lifetime is 10 billion years. So we're going to then multiply through by that, and we're going to get that the lifetime of Sirius is equal to 0.08 times 10 billion years, which is about 0.8 billion years, or 800 million years. So now I can take this and put it here. So what you can see is that the more massive a star is, the much more luminous it is. These low mass stars are much less luminous, and therefore the main sequence lifetimes of a more massive star are very short, while those of a less massive star are very long, which basically means that massive stars burn out really quickly and that low mass stars take a long time. This becomes important later because the more massive a star is, the more it shapes its environment around it after it burns out, and the more violently it explodes. And so they just become much more important in terms of the environment around them and the galaxy as a whole.